a radio telescope array in New Mexico picked up something impossible. During a routine systems test, engineers transmitted a calibration pulse toward empty space, a standard procedure. Meaningless noise meant to bounce off nothing. But 3I, Atlas, our third interstellar visitor, answered back. The return signal arrived precisely 2.7 seconds after transmission, modulated at frequencies no natural object should produce, carrying patterns that matched the test pulse with unsettling accuracy. Engineers triple-checked their equipment, ran diagnostics, and repeated the test. The response came again, stronger this time, as if the object had refined its reply. This wasn't an echo. This wasn't interference. This was a reaction, and it raised a question no one in the control room was prepared to answer. What happens when we accidentally contact something that's been listening all along? The accidental transmission. The very large array in Socorro operates on a rhythm most people never see. Between observation windows, when the facility transitions from one research program to another, engineers conduct routine system checks. These calibration sequences involve transmitting known signals into space, measuring how the equipment performs, and adjusting parameters before the next scientific campaign begins. The pulses themselves carry no information, just carrier waves at specific frequencies designed to test transmitter output, phase coherence, and timing accuracy across the array's 27 dish antennas. On the night in question, the VLA engineering team initiated a standard L-band calibration at 42 GHz, the hydrogen line frequency, chosen because it sits in a protected radio astronomy band with minimal terrestrial interference. The transmission lasted 18 milliseconds, delivered 500 kilowatts of peak power, and pointed toward a patch of sky the scheduling software had flagged as empty. No catalogue sources, no active observation targets, just blank space where the dishes could safely conduct their tests without contaminating ongoing research. The engineers logged the pulse, noted the equipment response, and moved on to the next frequency band. What they didn't account for was 3I, Atlas. The object had entered that supposedly empty region just 3 hours earlier, moving at 34 kilometers per second on its post-perihelion trajectory. At the moment of transmission, the comet sat 0.18 astronomical units from Earth, roughly 27 million kilometers, well within the VLA's effective range, but far enough to seem irrelevant to a routine calibration. The pulse spread as it traveled, weakening with distance according to the inverse square law, until it reached the vicinity of the interstellar visitor as a faint electromagnetic whisper barely distinguishable from the cosmic microwave background. Then, something unexpected occurred. The VLA's receiving systems, still active and monitoring during the calibration sequence, registered a return signal. The detection came 2.73 seconds after the original transmission, exactly the round-trip light time to 3I, Atlas and back. The signal arrived at 1.42 GHz, the same frequency as the test pulse, with a bandwidth that matched the calibration parameters to within 0.3%. Initial analysis suggested a reflection, perhaps off some unexpectedly metallic surface on the comet, but the signal strength didn't match that hypothesis. Reflected signals attenuate rapidly, losing power with each bounce. This return carried far more energy than a passive reflection should allow, roughly 40 times stronger than models predicted for a simple echo off ice and rock. The engineering team flagged the anomaly and requested a repeat test. 90 minutes later, with 3I, Atlas now 180,000 kilometers farther along its trajectory, the VLA transmitted an identical pulse toward the object's new position. The response came again, this time arriving 2.85 seconds after transmission, consistent with the increased distance. But the signal characteristics had changed. The return pulse showed phase modulation, subtle shifts in the wave's timing structure that weren't present in the original test signal. Frequency analysis revealed sidebands flanking the main 1.42 GHz carrier, spaced at intervals of exactly 16.16 Hz. That number stopped the analysis cold. It matched the comet's rotation period, converted to frequency. One cycle per 16.16 hours equals 16.16 MHz, and the sidebands appeared at precisely 1,000 times that value. A third transmission, conducted 4 hours after the second, produced a return signal with even more pronounced modulation. The phase shifts now formed a repeating pattern across the 18 millisecond duration, a structure that bore no resemblance to the flat, featureless test pulse. Spectral analysis isolated 7 distinct frequency components in the return signal, each separated by harmonics of the rotation-derived base frequency. This wasn't random noise. It wasn't an equipment malfunction. The signal structure implied processing, modulation applied after reception and before retransmission, characteristics inconsistent with passive reflection off inert material. By dawn, word had spread through the radio astronomy network. The VLA team prepared a formal anomaly report documenting signal parameters, timestamps, and equipment status. But even as they compiled the data, unease settled over the facility. The engineers had stumbled into a conversation they never intended to start, with an object whose nature remained deeply uncertain. And the most troubling detail sat in the raw data files. The third return signal had arrived 0.03 seconds earlier than the light travel time strictly allowed, as if 3I, Atlas, had begun transmitting before the test pulse reached it. Signal characteristics that don't add up. Radio signals from natural cosmic sources follow predictable patterns. Pulsars emit with clockwork regularity, their rotation stamped into every pulse. Masses produce coherent radiation through quantum processes that amplify specific frequencies. Even the chaotic emissions from active galactic nuclei show statistical properties that reveal their origins in plasma turbulence and magnetic reconnection. The return signals from 3I, Atlas, fit none of these templates. Instead, they displayed characteristics that radio engineers associate with artificial transmitters: precise frequency control, deliberate modulation, and adaptive behavior that changed across multiple transmissions. The first anomaly appeared in the signal's bandwidth. Natural radio sources either span broad frequency ranges, like thermal emission from hot gas, or concentrate at specific atomic transitions, like the hydrogen line itself. The 3I, Atlas returns, occupied a narrow band just 47 Hz wide, centered on the test pulse frequency with precision that required active frequency stabilization. Thermal radiation from the comet's surface, heated by solar proximity, should have produced emission across tens of megahertz. The jets, rich in ionized gas and plasma, should have generated synchrotron radiation spanning even wider ranges. Instead, the signal stayed locked within a bandwidth narrower than most commercial radio stations, suggesting a source that could control its output frequency to better than 1 part in 30 million. Polarization analysis revealed more problems for natural explanations. Radio waves carry orientation information in their electric and magnetic fields, and this polarization signature often reveals the emission mechanism. Synchrotron radiation from relativistic electrons in magnetic fields produces linear polarization aligned with the field direction. Thermal emission from rough surfaces generates unpolarized or weakly polarized signals. The 3I Atlas returns showed circular polarization, with the electric field vector rotating as the wave propagated. This characteristic appears in transmissions that pass through certain plasma regions or reflect off helical structures. But the degree of polarization, 94% across all three test responses, exceeded anything seen from natural cosmic sources. Laboratory measurements of circularly polarized emission typically require carefully designed antennas or specific crystal orientations, not the chaotic environment of a cometary coma. The phase modulation patterns added another layer of complexity. Radio engineers use phase modulation to encode information onto carrier waves, shifting the timing of wave peaks and troughs to represent data. Natural sources can show phase variations due to propagation effects or source motion, but these variations appear random or follow smooth, predictable curves. The modulation on the 3I Atlas signals formed discrete steps, with phase shifts occurring at regular intervals across the 18 millisecond pulse duration. Fourier analysis extracted the modulation pattern and found it repeated every 0.56 milliseconds, exactly 32 cycles within the pulse length. This regular structure, combined with the phase steps occurring at identical points in each response, suggested a modulation process controlled by some form of timing reference. Signal strength measurements compounded the mystery. The inverse square law dictates that radio signals weaken predictably with distance. A passive reflector, like a metallic sphere or a flat mirror, returns only a tiny fraction of the incident power, typically less than 1 part in 10 billion for objects the size of 3I Atlas at these distances. Yet the returned signals carried power levels indicating an effective radar cross-section of 130 square kilometers, far larger than the comet's physical size. This enhancement could only occur if the object somehow collected, amplified, and retransmitted the signal rather than simply bouncing it back. The required gain exceeded 1 million, comparable to transmitters used for deep space communications, not processes expected from ice and rock. Temporal analysis of the three responses revealed adaptive behavior. The first return matched the test pulse duration almost exactly. The second lasted slightly longer, 18.4 milliseconds, and included additional frequency components. The third extended to 19.2 milliseconds and carried the most complex modulation pattern. This progressive elaboration suggested a system that analyzed incoming signals and modified its responses based on what it received. Natural processes don't exhibit this kind of learning curve. Water ice doesn't improve its reflective properties after repeated illumination. Plasma doesn't develop more sophisticated emission patterns through practice. The engineering team constructed detailed models, attempting to explain each anomaly through conventional physics. Could unusual ice crystal orientations produce the observed polarization? The required crystal alignment would need to span thousands of kilometers and maintain perfect order despite the comet's rotation, physically impossible given measured temperature gradients. Could plasma instabilities in the jets generate the narrow bandwidth? Plasma emissions naturally broaden through Doppler shifts and turbulence, working against the observed frequency precision. Could the phase modulation arise from interference between multiple reflection points on an irregular surface? The modulation's regularity and progressive complexity ruled out random interference patterns. Each conventional explanation failed on quantitative grounds. The signal characteristics required mechanisms that natural cometary processes cannot provide. Frequency stabilization to parts per million, circular polarization approaching theoretical limits, power amplification by factors of millions, and adaptive modulation that grew more complex with each exchange. The VLA team documented these discrepancies in their technical report, noting that while each individual anomaly might find some exotic natural explanation, the combination of all characteristics in a single source pushed conventional physics beyond credible limits. The rotation lock mystery. Every return signal from 3i, Atlas, carried a signature embedded in its structure. Modulation sidebands spaced at exactly 16.16 Hz. This frequency appeared too precise to dismiss as coincidence. Converted back to a period, 16.16 Hz corresponds to one cycle every 61.87 milliseconds, but multiply by 1000, and the result is 61,870 milliseconds, or 1.0312 minutes, which scales to 61.87 minutes. The pattern breaks down. The correct conversion reveals the connection. The sideband spacing equals exactly 1000 times the comet's rotational frequency of 0.01716 Hz, derived from its 16.16-hour rotation period measured through photometric observations months earlier. This connection posed immediate questions. Why would a radio signal encode information about the source's rotation rate? Natural emission mechanisms don't typically stamp rotational frequencies onto their output in such explicit ways. Pulsars show rotation signatures because their emission beams sweep past Earth like lighthouse beacons. But 3i, Atlas, wasn't pulsing. It was responding to discrete transmissions with signals that contained rotational information encoded as frequency components. The process required some link between the object's physical rotation and the mechanism generating the radio returns. Researchers at the National Radio Astronomy Observatory constructed a detailed timeline comparing signal characteristics with the comet's known rotational phase. Photometric data from amateur observers provided continuous monitoring of 3i, Atlas's brightness variations, establishing its orientation at each moment with precision better than 5 degrees. The first VLA test occurred when the object's long axis pointed roughly 30 degrees away from Earth. The second test caught the comet rotated another 22.5 degrees, and the third transmission arrived when the axis pointed nearly edge-on to our line of sight. Yet all three return signals showed identical sideband spacing at 16.16 Hz, regardless of rotational phase. This consistency revealed something important. The rotation signature wasn't tied to viewing geometry or to specific surface features rotating in and out of view. Instead, it represented a fundamental property encoded into every response. The signal structure remained stable even as the comet's orientation changed by more than 45 degrees across the observation sequence. Whatever process generated the returns had access to information about the object's spin rate and embedded that information into the transmitted signal in a form that remained constant despite changing geometry. The team investigated whether natural rotational modulation could produce the observed pattern. As a comet spins, surface features move into and out of sunlight, creating brightness variations at the rotation frequency. Could this solar heating modulate the temperature of some reflective surface, which in turn affected the properties of returned radio signals? The numbers didn't support this mechanism. The timescale for thermal response in ice and rock exceeds hours, far too slow to create modulation at frequencies near 16 Hz. The comet's rotation period of 16.16 hours means surface features complete one cycle every 58,176 seconds, producing a fundamental frequency of 0.0000172 Hz, not 16.16 Hz. The sideband spacing was exactly 1 million times too fast to represent direct rotational modulation of any surface property. Alternative models explored whether plasma structures co-rotating with the nucleus could generate appropriate frequency signatures. The comet's jets and Coma contained ionized gas trapped in magnetic fields that might, in principle, rotate with the body. Plasma oscillations in such regions could produce radio emission at frequencies determined by local electron density and magnetic field strength. However, calculations showed that achieving 16.16 Hz oscillations would require magnetic fields exceeding 50 nanotesla and electron densities above 10 million particles per cubic centimeter conditions, found only deep within the Tesla. Sun's corona, not in cometary comas, where typical values run 100 times lower. The team then examined whether the signal analysis itself introduced the rotational frequency through data processing artifacts. Could the sideband spacing arise from interaction between the test pulse repetition rate and some characteristic timescale in the recording equipment? This hypothesis failed immediately. The three tests occurred at different times with different repetition schedules, yet all produced identical 16.16 Hz spacing. The frequency appeared in the raw voltage time series, before any processing, ruling out analysis artifacts. A more radical possibility emerged from the signal timing data. Each return pulse showed fine structure, rapid variations in amplitude and phase occurring within the 18 millisecond duration that repeated at intervals of 61.87 milliseconds. This represents exactly 1/1000th of the rotation period, suggesting the signal generation process operated on timescales 1,000 times faster than the comet's physical spin. The only way to connect these disparate timescales was through a mechanism that measured the rotation rate and used that measurement to control a much faster process, like a clock that keeps time, by counting rapid oscillations locked to a slower reference. Radio engineers recognized this architecture immediately. It's called a phase-locked loop, a circuit design where a fast oscillator synchronizes to a slower reference signal by continuously adjusting its frequency to maintain a fixed relationship. PLLs appear in everything from computer processors to radio receivers, but they require active electronic components, transistors, capacitors, feedback amplifiers, not the passive ice and rock that supposedly comprises 3I, Atlas. The signal characteristics pointed toward a system that sensed the rotation rate and deliberately encoded that information into its radio transmissions, using sophisticated frequency synthesis techniques found in engineered devices, not natural phenomena. Power budget impossibilities. Radio transmission consumes energy. Every watt radiated into space must come from somewhere, extracted from sunlight, chemical reactions, kinetic energy, or stored power. For the return signals from 3I, Atlas, the energy requirements exceeded what natural processes could plausibly deliver by factors that grew more troubling with each analysis. The power budget didn't just strain conventional explanations, it broke them entirely. The VLA receivers measured return signal strength at -192 decibels relative to 1 milliwatt, a tiny whisper of radio energy, but enough to calculate the total transmitted power using the known distance and antenna properties. The math is straightforward. At 27 million kilometers, even accounting for the VLA's large collecting area, the return signals required 3I, Atlas, to radiate approximately 340 watts of radio frequency power during each 18 millisecond response. That's 340 joules of energy per pulse, delivered in a precisely controlled narrow bandwidth at a specific frequency with complex modulation. The question became, where does that power come from? Solar energy represented the most obvious source. At 0.4 astronomical units from the Sun, the comet's distance during the tests, solar irradiance delivers about 8,600 watts per square meter. A perfectly efficient collector with an area of 0.04 square meters could gather 340 watts, but perfect efficiency doesn't exist. Real photovoltaic panels achieve 20 to 30% conversion, requiring collection areas around 0.15 square meters, plausible for engineered solar panels, impossible for ice spontaneously focusing sunlight. More critically, converting solar power to radio transmission demands additional components: voltage regulators, radio frequency oscillators, power amplifiers, antenna structures. Each conversion step loses energy, typically requiring input power 5 to 10 times larger than the radiated output. The actual solar collection area needed would exceed 1 square meter, and that's assuming technology comparable to human spacecraft designs. The team examined whether chemical energy stored in the comet's volatile ices could power the transmissions. Sublimation of water ice releases about 2,800 joules per gram. To generate 340 joules of radio energy at 10% efficiency would require vaporizing 1.2 grams of ice, not much mass. But the process must occur in 18 milliseconds, and couple that energy into radio frequency electromagnetic fields rather than random thermal motion. No known natural process achieves this conversion. Chemical reactions release energy as heat and kinetic energy of molecules. Transforming that into coherent radio waves requires antennas, transmission lines, and frequency-selective circuits that don't spontaneously form in cometary material. Mechanical energy from rotation offered another potential source. The comet's 16-hour spin period implies rotational kinetic energy determined by its moment of inertia. For a roughly spherical body 3 kilometers in diameter with density around 500 kilograms per cubic meter, typical of comets, the total rotational energy reaches approximately 100 trillion joules. This vast reservoir could power millions of radio pulses, but accessing rotational energy requires mechanisms that convert spin into electricity. Generators, turbines, or piezoelectric materials stressed by centrifugal forces. None of these exist in natural cometary material. Ice and rock don't generate voltage when they spin. The rotational energy remains locked in mechanical form, unable to power radio transmissions without elaborate conversion machinery. The research team then considered exotic natural phenomena. Could magnetic field interactions extract energy from the solar wind? At 0.4 astronomical units, the solar wind carries kinetic energy density around 0.01 joules per cubic meter, flowing past the comet at 400 kilometers per second. A perfect collector with a cross-sectional area of 10 square meters, sweeping up solar wind for 18 milliseconds, could gather at most 0.072 joules 1/5000th the required power. Could plasma instabilities in the Coma generate radio emission? Plasma does radiate when heated or compressed, but the emission spreads across broad frequency ranges and produces power levels thousands of times weaker than observed, not the narrow-band kilowatt-scale signals in the data. Each conventional source failed the power budget test. Solar collection required improbably large areas and sophisticated conversion technology. Chemical energy lacked coupling mechanisms to generate radio waves. Rotational energy needed generators that don't exist in natural materials. Electromagnetic extraction from space plasmas fell short by factors of thousands. The analysis pointed toward a conclusion the team hesitated to state explicitly. The observed radio transmissions required either unknown physics that somehow concentrates and converts energy with impossible efficiency, or they required engineered power systems comparable to those on artificial satellites. The temporal pattern of responses added another constraint. The 3 test pulses occurred over an 8-hour span, and 3 I Atlas replied to each with consistent power levels. If the object drew on stored energy, it possessed reserves sufficient for multiple full power responses with no measurable depletion. If it harvested energy from its environment, it maintained collection and conversion processes across changing solar distances and orientations. Either scenario demanded capabilities that passive natural objects simply don't display. Researchers calculated the minimum technological sophistication required to match the observed performance. A radio transmitter delivering 340 watts at 1.42 GHz with the measured bandwidth and modulation characteristics would require components with total mass around 2.5 kilograms, assuming technology similar to deep space probe transmitters. The power supply, whether solar panels or batteries, would add another 5 to 15 kilograms, depending on design. These masses are trivial compared to the comet's estimated multi-billion kilogram total, but they represent a completely different category of object. Natural comets don't carry radio transmitters, massing 8 kilograms. Spacecraft do. Frequency, precision beyond natural limits. The return signals from 3I Atlas maintained frequency, stability that natural emission processes cannot achieve. Measuring this stability required comparing the received frequency against atomic reference standards at the VLA, clocks accurate to 1 part in 10 trillion. The results showed that across each 18 millisecond pulse, the carrier frequency at 1.42 GHz varied by less than 0.5 Hz, a fractional stability of 3.5 parts in 10 billion. Across the 3 separate transmissions spanning 8 hours, during which the comet travelled 980,000 kilometers and rotated through 119 degrees, the center frequency remained constant to within 1.2 Hz. This performance exceeded the stability of the VLA's own local oscillators and approached the limits of what hydrogen maser clocks achieve. Natural radio sources don't display this kind of frequency control. Consider pulsars, often cited as nature's most precise clocks. These rapidly rotating neutron stars emit radio beams with periods stable to parts per trillion over years, but their emission spans bandwidth of tens to hundreds of megahertz. The stability describes the repetition rate, not the instantaneous frequency content. A pulsar's radio spectrum spreads broadly because emission arises from incoherent processes. Charged particles streaming through magnetic fields, each contributing slightly different frequencies that blur together. The result shows excellent timing stability but poor spectral purity. Thermal emission presents even worse frequency control. Any object above absolute zero radiates electromagnetic energy across a spectrum determined by its temperature. The Sun's surface at 5,800 Kelvin produces a broad spectrum peaking in visible light but extending from radio waves to X-rays. Cometary Coma temperatures near 200 Kelvin generate thermal emission peaking in the far infrared, but radio frequency thermal noise still appears across the entire radio spectrum with no particular preference for any specific frequency. Natural thermal processes simply cannot produce narrowband emission. The frequency width of thermal radiation scales with the temperature through Planck's law, and achieving Hertz-level bandwidth would require temperatures below 0.0001 Kelvin conditions not found anywhere in the solar system outside specialized laboratory experiments. Plasma emission mechanisms fare slightly better, but still fail the precision test. Maser's microwave amplification through stimulated emission of radiation can generate narrow-band signals when molecules in space transition between quantum energy levels. The hydroxyl radical maser at 1.665 GHz, common in star-forming regions and some cometary comas, produces emission lines just kilohertz wide. But even this impressive natural coherence falls short of the sub-hertz precision seen in the 3i. Atlas returns by factors of thousands. Moreover, master emission requires specific excitation conditions and produces signals at fixed frequencies determined by atomic physics, not frequencies matching whatever test pulse happens to arrive. The research team examined whether Doppler stabilization could sharpen the frequency. As a source moves, its emission frequency shifts toward blue for approaching motion, toward red for recession. If multiple emission regions on a rotating object moved with precisely balanced velocities, their Doppler-shifted frequencies might sum to create artificially narrow bandwidth. Detailed calculations showed this mechanism fails for 3i Atlas. The comet's rotation creates velocity differentials across its surface reaching 50 meters per second, which would Doppler shift 1.42 GHz emission by plus or minus 240 Hz, depending on location. Instead of narrowing the emission, rotation naturally broadens it through this velocity spread, exactly opposite the required effect. Measurement of the frequency stability across the 3 separate test responses revealed something even more remarkable. The return signals tracked the transmitted frequency with extraordinary fidelity. The VLA transmitters, locked to hydrogen maser references, maintained frequency accuracy to 0.02 Hz. The 3i Atlas returns matched this accuracy to within measurement precision, showing that whatever process generated the signals could somehow detect the incoming frequency and reproduce it with comparable precision. This represents a coherent response. The return signal maintains a phase relationship with the transmitted pulse, like an echo that preserves the timing structure of the original sound. Natural reflection can preserve frequency through elastic scattering, where photons bounce off surfaces without energy loss. But elastic scattering is an instantaneous process at atomic scales. The observed responses required 2.7 seconds minimum round-trip time, implying the signal traveled to 3i Atlas. Some process occurred, and a return traveled back. During those 2.7 seconds, the transmitted pulse had long since passed. Nothing remained for elastic scattering to reflect. Instead, the object must have absorbed the incoming signal, stored information about its frequency, and generated a new transmission matched to what it received, a process called coherent retransmission that requires active detection, memory, and frequency synthesis. Radio engineers employ coherent retransmission in transponders, devices that receive signals and retransmit them with precise frequency control. Transponders power satellite communications, radar beacons, and deep space tracking systems. They work through a chain of electronic components. A receiving antenna captures incoming radiation, a mixer circuit extracts frequency information, a phase-locked loop synthesizes a reference signal matching the received frequency, and a power amplifier drives a transmitting antenna. Each stage requires precise timing, temperature-stable components, and careful design to maintain frequency accuracy across the entire chain. These are not simple devices. They represent sophisticated radio frequency engineering, containing dozens of specialized components working in coordination. The frequency precision observed in 3i Atlas returns demanded either unknown natural physics that achieves frequency stabilization through mechanisms science has never observed, or it demanded engineered transponders comparable to those launched on human spacecraft. The team documented this dichotomy in stark terms. The measured frequency stability exceeded natural emission mechanisms by at least 4 orders of magnitude, and matched the performance characteristics of artificial radio systems designed for coherent signal processing. No middle ground appeared in the analysis. Either nature had hidden an exotic frequency locking process in cometary physics, or something artificial was operating in the vicinity of 3.1 Atlas. The amplitude modulation code. Beyond frequency, precision, and power levels, the return signals carried structure in their amplitude variations, patterns of stronger and weaker intensity occurring within each 18 millisecond pulse. Initial analysis dismissed these variations as noise or propagation effects, random fluctuations expected when radio waves traverse 27 million kilometers of space filled with solar, wind, plasma, and Earth's ionosphere. But detailed examination revealed something far more systematic. The amplitude variations, repeated across all 3 responses with striking consistency, forming a pattern that looked less like noise and more like deliberate modulation. Signal processing specialists at the Jet Propulsion Laboratory received the raw VLA data and applied correlation techniques designed to detect repeating structures hidden in apparent randomness. These methods, originally developed for extracting faint spacecraft signals from noise, search for any subsequence of samples that appears multiple times within a longer record. The results showed that each 18 millisecond return pulse contained a specific amplitude pattern that repeated internally at intervals of 0.56 milliseconds, exactly 32 complete cycles within the pulse. Duration. This repetition couldn't arise from random processes, which by definition don't produce exact copies of themselves. The pattern itself consisted of amplitude variations following a consistent envelope. 4 peaks of different heights, separated by lower intensity regions. Digital sampling of the signal captured these variations at 10 million samples per second, providing detailed amplitude measurements every 100 nanoseconds. Plotting the amplitude values revealed the structure clearly: 4 distinct maxima at relative heights of 1, 0.68, 0.45, and 0.73 inches standardized units, with intermediate regions dropping to about 0.15 of peak amplitude. This 4-peak pattern repeated precisely every 0.56 milliseconds across the entire pulse length, creating a highly regular structure imposed on top of the main carrier wave. Researchers investigated natural phenomena that might generate 4-peak amplitude patterns. Interference between multiple reflection points could create complex amplitude variations through constructive and destructive wave combination. But interference patterns shift continuously as geometry changes. The 3i Atlas pattern remained fixed across 3 separate observations spanning 8 hours and 980,000 kilometers of comet motion geometry that should have scrambled any interference pattern beyond. Recognition. Plasma turbulence in the signal propagation path could amplitude modulate radio waves passing through density fluctuations. But turbulence creates broadband random variations, not repeating patterns with precise timing. The 0.56 millisecond repetition interval provided a crucial clue. This period corresponds to a frequency of 1,785.7 Hz, exactly 110.5 times the 16.16 Hz sideband spacing already identified in the frequency spectrum. The amplitude pattern locked to the same rotational frequency signature embedded throughout the signal structure suggesting a common timing source controlled both frequency and amplitude modulation. But the connection ran deeper. 1785.7 Hz equals 2, 7.5 times 16.16 Hz, linking the pattern to a power of 2 multiple of the base frequency. This kind of harmonic relationship appears frequently in digital systems where clocks divide or multiply reference frequencies using binary counters, but not in natural phenomena where frequency ratios follow simpler integer relationships or remain unrelated. Information theorists examined whether the amplitude pattern could encode data. Radio communication systems use amplitude modulation, varying signal strength, to represent ones and zeros as a fundamental encoding method. The 4 distinct peak heights in the 3i Atlas pattern could represent a base 4 numerical system where each peak height corresponds to a different symbol, 0, 0, 0, 1, 10, or 11 inches binary notation. With 4 peaks per 0.56 millisecond cycle and 32 cycles per pulse, each 18 millisecond return could carry 128 symbols of information. This calculation assumed 1 symbol per peak, but more sophisticated encoding schemes could embed additional data in the timing between peaks or in subtle phase relationships, potentially increasing information content several-fold. The team attempted to decode the amplitude pattern under various assumptions about the encoding scheme. If the pattern represented binary data, the 4 peak heights might correspond to 2-bit values, with 1 representing 11, 0.73 representing 10, 0.68 representing 01, and 0.45 representing 00. Applying this decoding to the first response generated a sequence of 128 2-bit symbols. The sequence showed non-random structure. Certain symbol combinations appeared more frequently than chance would predict, and specific subsequences repeated at irregular intervals. These characteristics matched what information theorists call low entropy, data information containing patterns and redundancy rather than pure randomness. Comparing the decoded sequences from all 3 responses revealed both consistency and variation. The first 32 symbols matched exactly across all 3 pulses, suggesting a fixed header or identifier. The remaining 96 symbols differed between responses, changing in ways that correlated with observable parameters: the comet's distance from Earth, its rotational phase angle, and the precise frequency of each test transmission. This correlation implied the varying portion carried information about the source's state or its measurement of external conditions, exactly what would be expected from a telemetry system reporting sensor data or system status. Cryptographic analysis searched for mathematical relationships within the decoded symbol sequences. Simple patterns emerged. Every 8th symbol in the varying portion followed a predictable increment, counting upward through values until wrapping back to 0 after reaching 3, consistent with a counter variable tracking some internal cycle. Other symbols appeared to encode the rotation phase, matching the photometrically determined orientation to within the resolution of the 4-symbol encoding. A third set of values correlated with the round-trip light time, suggesting distance measurement. The patterns were subtle but systematic, displaying the hallmarks of structured data rather than meaningless noise. The most startling discovery came from examining the amplitude pattern's phase coherence with the carrier wave. Detailed analysis showed that the amplitude peaks occurred at specific points in the carrier wave cycle, always at the same phase angle relative to the 1.42 GHz oscillation. This phase locking required the amplitude modulation process to maintain precise timing synchronization with the carrier frequency, a technical requirement that demands sophisticated signal generation hardware. Natural processes don't maintain phase relationships across 6 orders of magnitude. In frequency, the carrier at 1.42 GHz and the modulation at 1.78 kHz represent vastly different timescales. Yet both lock together with sub-degree precision throughout the 18 millisecond duration. Engineers recognize the signature of digital signal synthesis, where computer-controlled waveform generators create radio signals by calculating amplitude values sample by sample using numerical algorithms. Modern software-defined radios work exactly this way, generating modulated carriers through digital computation rather than analog electronics. The phase-locked amplitude pattern pointed toward a signal generation architecture that computed both carrier and modulation digitally, maintaining mathematical relationships between frequency components through precise numerical control, a level of sophistication found in designed systems, not natural radio sources emerging from cometary ice. Adaptive response patterns. The 3 VLA test transmissions didn't just provoke responses from 3i Atlas, they triggered progressively more complex returns that suggested learning or adaptation. This evolution in signal characteristics across successive exchanges raised questions that went beyond mere anomaly classification and entered territory that made researchers profoundly uncomfortable. The possibility that whatever generated the signals was refining its behavior based on experience. The first test transmission lasted exactly 18 milliseconds and carried a simple, continuous wave tone at 1.42 GHz. The return signal matched this duration precisely, lasting 18.03 milliseconds, with measurement uncertainty of plus or minus 0.05 milliseconds. The slight duration, excess 30 microseconds, seemed negligible, well within natural variation or timing jitter. The signal contained the frequency sidebands and amplitude pattern already described, but both appeared relatively simple. Just 3 primary sideband pairs flanking the carrier and an amplitude pattern with modest variation between peaks. The second test occurred 90 minutes after the first. Engineers intentionally modified the transmission, extending duration to 20 milliseconds and adding low-level frequency modulation, a 2 Hz sinusoidal variation in carrier frequency, meant to test how the response would handle more complex input. The return signal surprised the team by lasting 20.8 milliseconds, not only matching the new input duration, but exceeding it by 800 microseconds, 27 times the excess seen in the first response. More striking, the return signal now contained 7 sideband pairs instead of 3, and the amplitude pattern displayed 6 peaks per cycle rather than 4. The object hadn't merely reflected the more complex input, it had elaborated on it, adding structure that wasn't present in the transmitted test. 4 hours after the second test, engineers transmitted a third pulse, this time incorporating both amplitude and phase modulation, a test pattern that varied both the signal strength and timing structure in a pseudo-random sequence used for radar imaging. This represented significantly more complex input than either previous transmission. The return signal stretched to 22.1 milliseconds, now exceeding the 19 millisecond input by 3.1 milliseconds. Spectral analysis revealed 11 sideband pairs, and the amplitude pattern showed 8 distinct peaks per cycle arranged in a configuration that bore no resemblance to the transmitted test pattern structure. The response had grown far beyond mere replication or reflection. It displayed elaboration that added information content with each exchange. Researchers plotted the progression, response complexity increasing systematically from test 1 through 3, with each return showing roughly 1.5 to 1.7 times the structural complexity of its predecessor. This scaling didn't match any physical model of passive reflection or natural emission. Reflected signals maintain or lose structure through scattering and dispersion. They don't gain detail. Natural emission processes follow fixed patterns determined by source conditions. They don't elaborate progressively in response to varying stimuli. The team considered whether the increasing complexity arose from the comet's changing geometry or environment. Between tests, 3I, Atlas, rotated through substantial angles and moved significant distances, altering its orientation and distance from both the Sun and Earth. Could these changes have modified some natural emission process to produce the observed progression? Detailed modeling showed that geometric and environmental factors should work against increasing complexity. As the comet rotated, any fixed surface features would have changed their view angle, potentially reducing signal coherence rather than enhancing it. Increasing distance should have weakened the return signals and made fine structure harder to detect, not easier. Communication theorists recognized the pattern. It resembled protocol negotiation in artificial communication systems. When two radios establish contact, they often exchange increasingly complex test messages to determine each other's capabilities, bandwidth, modulation schemes, error correction methods. Each radio responds to the other's test with a more sophisticated reply, demonstrating it can handle complex signals and establishing parameters for efficient data exchange. The progression seen in the 3I Atlas responses matched this kind of handshaking sequence, with each return effectively saying, "I received your message and can respond with something more complex." The timing of elaborations provided another clue. The 90-minute gap between test 1 and 2 allowed 3I Atlas to travel 180,000 kilometers and rotate through 33.5 degrees. The 4-hour gap before test 3 covered 490,000 kilometers and 148.4 degrees of rotation. Yet the response complexity increased steadily despite these wildly different intervals and geometric changes. The progression appeared to depend on the sequence of exchanges first, second, third, rather than on elapsed time or cumulative rotation. This sequence-dependent behavior suggested memory. The system generating responses somehow retained information about previous exchanges and used that history to shape subsequent returns. Neurobiologists noted parallels to synaptic plasticity, the process by which neural connections strengthen with repeated activation. Biological learning systems often show similar progressive elaboration, where repeated stimulation leads to increasingly complex responses as the system develops internal representations of stimulus patterns. But biological learning operates through molecular changes in cell structures, requiring proteins, membranes, and genetic control mechanisms, components that certainly don't exist in cometary ice. If the 3I Atlas responses demonstrated learning, it would have to occur through completely different mechanisms. The alternative explanation demanded serious consideration. The responses came from a system designed to analyze incoming signals and adapt its behavior accordingly. Modern cognitive radios use exactly this approach, employing machine learning algorithms to optimize transmission parameters based on signal environment and detected patterns in received data. These systems adjust frequency, modulation, power, and duration dynamically to maximize communication efficiency. The progression of 3I Atlas responses displayed precisely this kind of adaptive optimization, with each return incorporating structural improvements that made it more distinguishable from noise and potentially more information-rich. Engineers calculated the minimum computational resources required to implement adaptive signal processing comparable to what the observations suggested. A basic system capable of receiving radio signals, extracting parameters like frequency and duration, and generating modulated returns with incrementally increased complexity would require a processor running at least several million operations per second, along with memory sufficient to store parameters from previous exchanges, perhaps a few kilobytes. By modern standards, this represents trivial computational power, easily achieved by processors massing under 1 gram. But for natural processes in a comet, it represents an unbridgeable gap. Ice crystals don't compute. Rock doesn't store data. Plasma doesn't run algorithms. The adaptive response pattern forced a stark conclusion onto the analysis. Either nature possesses completely unknown mechanisms that allow inert matter to display learning-like behavior through processes that mimic computation and memory, or the radio returns from 3I, Atlas, originated from a system capable of information processing, a system that could receive, analyze, remember, and adapt. The data left no middle ground. The Doppler shift paradox. Radio signals from moving sources undergo frequency shifts due to the Doppler effect, a phenomenon so fundamental and well established that astronomers use it to measure velocities of everything from nearby planets to distant galaxies. As 3I, Atlas, traveled through space at 34 kilometers per second, its radio emissions should have been Doppler shifted by an amount precisely calculable from special relativity. The observed shifts violated these calculations in ways that suggested the source possessed real-time knowledge of its own velocity relative to Earth. Basic physics predicts the Doppler shift for radio signals. When a source moves toward an observer, received frequency increases by a factor of 1 plus v, c, where v is the velocity along the line of sight and c is the speed of light. For 3I, Atlas, approaching Earth at 34 kilometers per second, this yields a fractional frequency shift of 34,000 divided by 300 million, or 0.000113. Applied to the 1.42 GHz carrier, the expected Doppler shift is 161 Hz toward higher frequency. Yet, the observed return signals arrived at 1.42000008 GHz, only 82 Hz above the transmitted frequency, roughly half the predicted shift. The team initially suspected measurement error or data processing mistakes. Multiple independent analyses confirmed the frequency measurements to better than 1 Hz precision. The reduced Doppler shift was real, repeatable, and present in all 3 test responses. More detailed examination revealed something even stranger. The Doppler shift varied systematically across the 3 observations in a way that tracked the changing Earth-comet velocity more accurately than the simple prediction based on the comet's orbital motion alone. Between Test 1 and Test 3, 3I, Atlas's velocity relative to Earth changed by 1.8 kilometers per second due to the combination of the comet's orbital motion and Earth's rotation. This velocity change should have altered the Doppler shift by 8.5 Hz across the 8-hour observation span. The measured shift change was 8.3 Hz, matching expectation to within 3%. But here's the paradox. If the return signals arrived with only half the expected absolute Doppler shift, why did the relative change match predictions so precisely? The answer pointed toward active frequency compensation. Radio engineers use Doppler compensation routinely in satellite communications. When a satellite moves relative to a ground station, onboard transponders measure the received frequency shift and adjust their transmission frequency to offset the Doppler effect. ensuring signals arrive at the intended frequency. This technique requires the transmitter to know both the received frequency, which is Doppler shifted from the ground transmitter's perspective, and the desired transmission frequency, which must be pre-shifted to counteract the motion. The math is straightforward, but demands real-time velocity knowledge. The spacecraft must determine how fast it's moving relative to the receiver and apply appropriate frequency corrections. The 3i, Atlas, returns displayed exactly this signature. The signals arrived Doppler shifted by roughly half the amount expected from a passive reflector, but the shift tracked velocity changes correctly across time. This combination is impossible for simple reflection. A mirror doesn't know how fast it's moving and can't adjust the frequency of light it reflects. It requires active sensing of velocity and deliberate frequency adjustment to compensate for motion. The observed behavior matched what engineers call two-way Doppler tracking, where a transponder removes the received Doppler shift and applies an equal and opposite shift to its transmission, effectively cancelling half the total Doppler effect. The precision of this compensation provided another clue. Achieving the observed frequency accuracy required velocity knowledge accurate to about 200 meters per second, a small error given the 3-4 kilometer per second total velocity. But measuring velocity with this precision from aboard a rapidly moving object demands sophisticated sensors. Options include Doppler radar ranging to nearby objects, star tracking for inertial velocity determination, or analysis of received signals themselves to extract Doppler information. All methods require power, computation, and precise timing resources not available to ice and rock tumbling through space. Researchers investigated whether some natural process could mimic Doppler compensation. Could preferential emission directions on a rotating comet create apparent frequency shifts different from simple motion-based predictions? Modeling showed that such effects produce deviations of order 0.01 Hz, at most negligible compared to the observed 79 Hz discrepancy. Could plasma motions in the Coma add velocity components that partially cancelled the orbital Doppler shift? The required plasma velocities would exceed 12 km per second toward Earth, speeds that would have been obvious in spectroscopic observations, which showed typical expansion velocities below 1 km per second. The paradox deepened when the team examined the frequency shifts on the individual sideband components flanking the carrier. Each sideband showed Doppler shifts consistent with the same velocity but slightly different absolute frequencies. The shifts scaled precisely with frequency. Sidebands at 1.41999 GHz showed proportionally reduced Doppler effect compared to the 1.42 GHz carrier, exactly as expected if all components underwent identical velocity-dependent frequency compensation. This frequency-dependent scaling ruled out propagation effects or instrumental artifacts, which would affect all frequencies identically. The compensation had to occur at the source, applied independently to each spectral component before transmission. Engineers calculated the processing requirements for multi-component Doppler compensation. The system would need to detect the incoming signal and measure its frequency, compute the Doppler shift by comparing received frequency to an internal reference, calculate the inverse shift required for transmission, and apply appropriate frequency corrections to each sideband independently. This sequence requires signal processing capability comparable to digital radio receivers, with analog to digital converters sampling at megahertz rates, fast Fourier transform processors analyzing spectral content, and numerical computation engines calculating frequency corrections. Total computational load would reach tens of millions of operations per second, again, trivial for modern electronics, but absolutely impossible for natural cometary material. The Doppler shift paradox presented one of the clearest signatures of intentional signal processing in the entire dataset. Unlike other anomalies that might admit exotic natural explanations involving unknown physics, Doppler compensation has no natural analogue. Passive objects cannot measure their own velocity and adjust their emission frequencies accordingly. Physics doesn't allow it. Only active systems with sensors, processors, and frequency-agile transmitters can implement this kind of sophisticated motion compensation. The 3i Atlas returns displayed unmistakable evidence of exactly these capabilities. Timing precision at the microsecond scale. The return signals arrived with timing precision that challenged even optimistic estimates of what natural processes could achieve. Measuring this precision required correlating received signals with atomic clock references accurate to nanoseconds, then analyzing timing variations across multiple observations. The results revealed consistency at the microsecond level far beyond what random reflection or plasma emission should produce, and approaching the timing accuracy of engineered transponder systems. Each VLA test transmission was time-stamped using hydrogen maser clocks that drift less than 1 nanosecond per hour. The receiving systems recorded return signal arrivals using the same clock reference, providing absolute timing accuracy better than 10 nanoseconds. Subtracting transmission time from reception time and accounting for the round-trip light travel distance gave the signal delay a measurement that should equal twice the Earth-comet distance divided by the speed of light. For 3i Atlas at 27 million kilometers, light travel time each way is 90 seconds, making the expected round-trip delay 180 seconds, or 2.73 minutes. The first return arrived 2.727 minutes after transmission, matching prediction to within 0.03% once corrections for Earth's rotation and comet motion during signal travel were applied. But the second and third returns showed something remarkable. They arrived with timing errors of just 42 and 38 microseconds, respectively less than 1 part in 4 million relative to the predicted delay. This consistency implied the return signals departed 3i Atlas at precisely the moment needed to account for its motion during the signal round trip, maintaining timing accuracy comparable to GPS satellite signals. Natural reflection produces timing scatter due to multiple propagation paths through irregular surface features. A radar pulse bouncing off a rough comet surface generates returns spread across microseconds to milliseconds as signals scatter from different surface points at varying distances. Plasma emission shows even worse timing coherence, with turbulent fluctuations causing arrival time variations at the millisecond scale. The 3i Atlas returns displayed none of this scatter, arriving as crisp pulses with rise times under 5 microseconds and timing jitter below the measurement precision. The timing precision demanded more than just a reflective surface. It required the source to respond at a precisely controlled moment after receiving the test pulse. Consider the sequence. Transmission leaves Earth at time t0, travels 90 seconds to the comet arriving at t0 plus 90. Some process occurs, a return signal departs at time t1, travels 90 seconds back and arrives at Earth at t1 plus 90. For the return to arrive 180 seconds after t0, the source must respond precisely at t0 plus 90 with 0 additional delay. Achieving this demands knowing when the signal arrived, processing that information essentially instantaneously, and initiating transmission without measurable latency. Engineers recognize this architecture as bent pipe transponder operation, where received signals trigger immediate retransmission through rapid electronic switching. Modern transponders achieve response times below 1 microsecond through high-speed signal processing circuits. But even these systems introduce some delay, typically 5 to 50 microseconds between reception and retransmission, due to amplifier response times and signal routing through circuit paths. The 3i Atlas returns showed delay times consistent with the light travel distance alone, implying the response mechanism added less than 40 microseconds of processing latency. This level of performance required either near instantaneous electronic switching or a mechanism that somehow anticipated the signal arrival and pre-staged its response. The research team investigated whether relativistic effects could sharpen the apparent timing. At 34 kilometers per second, special relativity introduces time dilation factors of order 1 part in 10 billion, far too small to explain microsecond scale precision. Could gravitational time dilation near the Sun affect signal timing? At 0.4 AU, solar gravitational effects reach about 1 part per billion, again negligible. Could the precision arise from signal averaging or correlation artifacts in data processing? Each test involved single transmissions, ruling out averaging. Correlation techniques measured arrival times from individual pulses without enhancement from repeated observations. The timing precision correlated with distance in a revealing way. As 3i Atlas moved farther from Earth between tests, the round-trip light time increased by 0.24 seconds due to the additional 36,000 kilometers of travel distance. The measured delay increased by exactly 0.237 seconds, matching the distance change to within 1.3%. This accurate tracking of changing distance implied the response mechanism somehow maintained constant actual delay time, under 40 microseconds, while the signal propagation delay varied by hundreds of milliseconds. Only a system that measured incoming signal timing and adjusted response timing accordingly could achieve this kind of distance-independent precision. Further analysis examined timing variations within each 18 millisecond pulse. The amplitude modulation pattern repeated every 0.56 milliseconds, with timing, precision, better than 200 nanoseconds, 1 part in 3,000, relative to the pattern period. This internal coherence required all modulation cycles to maintain synchronized timing throughout the pulse duration, suggesting a stable master clock controlled the entire signal generation process. Frequency synthesizers in human-designed radios use crystal or atomic oscillators, providing exactly this kind of timing reference, generating signals with phase coherence maintained across arbitrary durations. The team calculated the required clock stability to produce the observed timing precision, a 200 nanosecond timing error over 0. 56 milliseconds implies fractional frequency stability of 3.6 times 10 negative 4, achievable with modest quality quartz crystals. But maintaining this stability across environmental temperature variations as the comet rotated through sunlight and shadow required either extreme temperature insensitivity or active temperature compensation. Natural crystals exist in cometary material, but they don't function as precision oscillators. Quartz crystals used in clocks require specific cuts, electrode coatings, and mounting arrangements to provide stable frequencies, none of which form spontaneously in space. The microsecond timing precision joined the growing list of signal characteristics that defied natural explanations. Each individual anomaly might stretch conventional physics. The combination of precise timing, Doppler compensation, frequency stability, adaptive modulation, and power requirements exceeded what any credible natural model could accommodate. The timing data, particularly troubled researchers because timing precision is difficult to fake or misinterpret. Unlike frequency measurements that might suffer from calibration errors or power calculations that depend on uncertain assumptions, timing is absolute. The signals either arrived when measured or they didn't. The consistency across three separate observations, the accurate tracking of changing distance, and the internal phase coherence all pointed unambiguously toward a source employing precision timing references found in engineered systems, not natural astronomical objects. Spectroscopic signatures in the carrier. While most analysis focused on the radio return signal's temporal and frequency structure, a parallel investigation examined the spectral purity of the carrier wave itself, the 142 GHz center frequency around which all other features were organized. Spectroscopic analysis at unprecedented resolution revealed that this carrier displayed characteristics suggesting phase-locked generation rather than natural emission, with sidebands and harmonics that painted a picture of digitally synthesized radio frequency waveforms. High-resolution spectroscopy requires analyzing signals at frequency scales far finer than the carrier frequency itself. The VLA processing pipeline recorded raw voltage samples at 10 million samples per second, capturing signal variations on timescales of 100 nanoseconds. Applying fast Fourier transforms to millions of samples simultaneously provided frequency resolution better than 0.001 Hz, allowing researchers to examine the carrier's spectral structure with exquisite detail. The resulting spectra revealed that the 1.42 GHz carrier wasn't a single pure tone, but rather a narrow cluster of frequencies spanning just 0.4 Hz, organized in a distinctive pattern. The carrier showed a central peak flanked by symmetrical sidebands spaced at exactly 60 Hz above and below center frequency. These primary sidebands themselves carried secondary sidebands at 16.16 Hz spacing, the rotational frequency signature present throughout the signal architecture. This hierarchical structure, where modulation at one frequency creates sidebands that themselves show modulation at different frequencies, appears in signals generated by cascaded mixing processes or digital frequency synthesis. Natural emission typically produces either pure spectral lines from atomic transitions or broad continuous spectra from thermal or non-thermal radiation, not nested sideband hierarchies. The 60 Hz primary sideband spacing immediately caught attention because 60 Hz is not a natural frequency related to cometry physics. It does, however, represent the power line frequency used throughout much of the world, raising suspicions about terrestrial interference. The team conducted extensive tests to rule out local interference. Observations of blank sky regions showed no 60 Hz components, and the sidebands appeared only during return signal reception, not in the intervals between transmissions. Moreover, the 60 Hz spacing remained constant across all three test responses, despite the comet moving nearly 1 million kilometers interference from Earth would vary as the geometry changed. The sidebands originated at the source, not from terrestrial contamination. This left a puzzle. Why would a signal from 3i, Atlas, display 60 Hz modulation? One hypothesis suggested the presence of rotating machinery at the source, operating at 3,600 revolutions per minute, a common industrial rotation rate for generators and motors. If some mechanical system at the source rotated at this rate, vibration or magnetic field variations could modulate the radio transmission at the rotation frequency. But 3i Atlas itself rotates once every 16.16 hours, not 60 times per second. Any rotating component would need to spin independently of the main body, requiring bearings, supports, and power sources to maintain rotation mechanical complexity that certainly doesn't exist in natural comets. Further spectral analysis revealed phase noise characteristics, random frequency fluctuations that appear in all real oscillators due to thermal effects and electronic component limitations. Every radio transmitter shows phase noise forming a skirt around the carrier frequency, with noise power decreasing at greater frequency offsets. The 3i Atlas carrier displayed phase noise with a specific profile, approximately minus 40 decibels per hertz at 100 Hz offset from the carrier, improving to minus 60 decibels per hertz at 1000 Hz offset. These values match the phase noise performance of synthesized signal generators using voltage-controlled oscillators with phase-locked loops common in engineered radio systems but not in natural processes, which either show zero phase noise, atomic transitions, or enormous phase noise, plasma emission. The spectroscopic team measured another telling characteristic. The carrier frequency drifted at a rate of 0.005 Hz per minute across the 8-hour observation span, a total drift of 2.4 Hz. This drift rate corresponded to a fractional frequency change of 1.7 parts per billion per hour, matching the thermal drift characteristics of high-quality temperature-compensated crystal oscillators. Natural masers locked to atomic transitions show no frequency drift. Their emission frequencies are fixed by quantum mechanics. Natural plasma oscillations vary at rates thousands of times faster, responding to density and temperature fluctuations at second timescales. The observed, slow, steady drift pointed toward a temperature-sensitive oscillator with modest thermal stabilization, exactly what would be expected from a spacecraft transmitter using crystal-controlled frequency generation. Harmonic analysis extended the investigation beyond the fundamental one, 42 GHz carrier, to search for harmonics at integer multiples of the carrier frequency. Radio transmitters often generate harmonics due to nonlinearities in amplifier circuits, producing signals at 2 times, 3 times, 4 times the fundamental frequency. The VLA's receivers covered only the L-band from 1 to 2 GHz, but coordinated observations with the Green Bank telescope extended coverage to 4 GHz. These observations detected a weak signal at 2.84 GHz, exactly twice the carrier frequency, with power about minus 35 decibels below the fundamental. This second harmonic showed the same modulation characteristics as the main signal, including the 16.16 Hz sidebands and the amplitude pattern, confirming it originated from the same source. The presence and relative strength of the second harmonic provided information about the transmission system's design. A ratio of minus 35 decibels between fundamental and second harmonic matches the performance of Class A or Class AB power amplifiers, common in radio transmitters where linearity is prioritized over power efficiency. More efficient amplifier designs like Class C or switching amplifiers generate stronger harmonics, while perfect linear amplifiers would produce no harmonics at all. The observed harmonic level suggested a transmitter designed with a specific balance between power efficiency and signal quality, a design choice made by engineers, not a characteristic emerging from natural physics. The research team constructed a detailed model of the spectroscopic signatures, incorporating the carrier purity, sideband structure, phase noise profile, frequency drift, and harmonic content. They compared this model against spectroscopic databases containing measurements from every known class of natural radio source: pulsars, masers, thermal emitters, synchrotron sources, and plasma oscillations. No natural source matched more than 2 of the observed characteristics. Pulsars showed excellent frequency stability, but different sideband structures. Masers displayed narrow line widths, but no harmonics. Thermal sources produced appropriate phase noise, but couldn't explain the hierarchical sidebands. Every natural comparison failed comprehensively. The model did match one comparison case nearly perfectly: the spectroscopic signature of the Voyager 1 spacecraft transmitter, measured during routine communications in 2024. Voyager's X-band transmitter, at 8.4 GHz, shows hierarchical sidebands from clock mixing processes, phase noise from its voltage-controlled oscillator, frequency drift from temperature variations as the spacecraft rotates, and harmonics from its traveling wave tube amplifier. Scaling Voyager's characteristics from X-band to L-band and accounting for different transmitter power levels produced a predicted spectrum almost indistinguishable from the 3i Atlas carrier. The spectroscopic signatures pointed unambiguously toward a radio transmission system architecturally similar to those aboard deep space probes. The silence from official channels. As data from the 3 VLA tests accumulated and independent analyses converged on the same troubling conclusions, a different pattern emerged in how information flowed through official channels. Radio astronomy facilities coordinate observations through formal scheduling processes, with results typically moving rapidly from telescope to archive to publication. The 3i Atlas data followed no such trajectory. Instead, it encountered delays, classification reviews, and institutional silences that frustrated researchers and fueled speculation. The first delay appeared within 48 hours of the initial observation. The VLA engineering team completed their preliminary analysis and prepared to submit the results to the Astronomers Telegram, a rapid communication service where astronomers announce transient discoveries and unexpected phenomena. This standard practice allows the global community to respond quickly with follow-up observations. But before submission, the draft report was flagged for review by the National Science Foundation's Office of Legislative and Public Affairs, an unusual step for a technical engineering report about system calibration tests. The NSF review took 11 days, during which the data remained restricted to the original engineering team and a handful of facility administrators. Leaked emails from this period, later shared anonymously through astronomy forums, revealed internal debate about whether the observations represented a genuine discovery or an artifact requiring deeper investigation before public disclosure. One email chain discussed the potential for misinterpretation by non-expert audiences and the need to prevent unwarranted speculation about the source's nature. By the time NSF cleared the report for submission, the astronomical optimal window for immediate follow-up had passed, 3i. Atlas had moved beyond easy reach of several major facilities. The published Astronomer's Telegram, when it finally appeared, focused almost entirely on the technical details of the VLA calibration sequence and mentioned the return signals only briefly as an anomalous radio detection requiring further investigation. The report included signal parameters and arrival times, but omitted the frequency precision measurements, adaptive response patterns, and Doppler compensation analysis that later analyses would highlight. Several astronomers noted the unusually sparse technical content, with one commenting publicly that the telegram reads like a legal document crafted to say as little as possible while technically disclosing a discovery. Follow-up observation proposals submitted to major facilities encountered unexpected obstacles. The Arecibo Observatory, despite its closure years earlier, appeared on paperwork as unavailable for this target, even though several smaller dishes remained operational for special observations. The Green Bank telescope granted only 4 hours of observing time spread across non-contiguous blocks, insufficient for detecting the patterns that required continuous monitoring. The European VLBI network initially approved a proposal for coordinated observations, but withdrew approval 3 days before scheduled observations, citing unspecified scheduling conflicts. A pattern emerged. Facilities capable of detecting and analyzing detailed signal structure found themselves unavailable, while observations that did proceed generated data sufficient to confirm the anomaly, but insufficient to characterize it fully. NASA's response added to the official silence. Despite multiple spacecraft having potential capability to detect radio signals from 3I Atlas, including Mars Reconnaissance Orbiter and the Deep Space Network's research receivers, no agency announcements confirmed any attempts at observation. Freedom of information requests filed by journalists and researchers seeking details about potential NASA monitoring were met with responses claiming no relevant records existed. Yet informal conversations with engineers at JPL and Goddard revealed that internal discussions about observing the object had occurred, with at least 2 preliminary observation plans drafted before being indefinitely postponed at the direction of headquarters. International coordination, typically robust for observations of rare interstellar objects, showed unusual fragmentation. The European Space Agency's tracking stations maintained public schedules showing no observations of 3I Atlas, despite the object passing through favorable positions for their antenna locations. The Russian Academy of Sciences radio astronomy facilities, usually quick to announce results from transient observations, released no data, despite confirmed observations mentioned in internal conference presentations later leaked to Western colleagues. China's Fast Radio Telescope, the world's largest single-dish instrument, conducted observations that were mentioned in a brief Chinese-language technical report, but never followed by detailed data release or English-language publication. The institutional silence wasn't total data did emerge, but through unconventional channels. Amateur radio astronomers with access to university facilities shared observations through online forums, bypassing traditional publication pathways. Graduate students anonymously posted analysis code and preliminary results to scientific preprint servers, generating discussion that official channels avoided. Retired astronomers with no institutional constraints spoke more freely at conferences, presenting findings that active researchers mentioned only obliquely or withheld entirely. This pattern created a fractured landscape where information existed but remained scattered, difficult to synthesize, and easy to dismiss as unvetted speculation. The most striking silence came from SETI institutions. The SETI Institute, Breakthrough Listen, and university-affiliated search programs typically maintain public observing logs and release data from candidate signal detections within months. Several of these facilities observed 3I Atlas during the critical period when the VLA tests occurred. Breakthrough Listen's observations at Green Bank overlapped with the second VLA test by 20 minutes, placing their instruments in position to detect any return signal. Yet no public data release followed, and inquiries about results received responses, noting only that analysis is ongoing, or that no definitive techno-signatures were identified, language that carefully avoided confirming or denying detection of signals. Internal documents obtained through confidential sources revealed the reasoning behind some institutional caution. One memo from an NSF program director noted concerns that premature announcement of ambiguous results could undermine public confidence in the scientific process, and emphasized the need for extraordinary evidence for extraordinary claims. Another document from NASA's Planetary Science Division discussed national security implications of detecting artificial signals from interstellar objects, and referenced consultations with the Department of Defense about appropriate disclosure protocols. The picture that emerged showed institutions wrestling with unprecedented questions about how to handle data that didn't fit comfortable categories. The official silence had measurable effects on scientific progress. Without coordinated follow-up observations, opportunities to test hypotheses and gather additional data were missed. Without open data sharing, independent verification of results became impossible. Without frank discussion in professional venues, the informal whisper network became the primary information channel, mixing genuine findings with speculation and rumor. The vacuum created by institutional caution filled with exactly the kind of uncontrolled speculation that the caution aimed to prevent. By late in the observing season, as 3I, Atlas, receded beyond easy reach of Earth-based facilities, the official position had crystallized around a careful non-statement. The radio detections represented an interesting anomaly requiring further study, with natural explanations remaining possible but not yet confirmed. This position satisfied no one, neither researchers convinced they had detected something extraordinary, nor skeptics who wanted definitive proof the signals arose from mundane causes. The silence from official channels achieved only one thing with certainty. It ensured that when the next interstellar visitor appeared, the response would be coloured by memories of missed opportunities and questions left unanswered. Signal correlation with rotation phase. The 16.16-hour rotation period of 3I, Atlas, measured through photometric observations, provided a testable prediction. If the radio signals originated from specific locations on the surface, their characteristics should vary systematically as the body rotated. A jet or reflective patch fixed to the surface would move into and out of optimal orientation relative to Earth, modulating signal strength and possibly altering other parameters. The VLA observations, coordinated with amateur photometric monitoring, allowed researchers to test this prediction with unprecedented precision. The results defied simple surface-based explanations. The first VLA test occurred when 3I, Atlas, presented its rotational phase at 127 degrees, placing one of the prominent dust jets identified in optical images roughly 30 degrees away from optimal Earth-facing orientation. Light curve models predicted this geometry should produce a brightness about 85% of maximum. The second test caught the rotation at 208 degrees, with no major surface features favourably oriented, a configuration expected to show minimal optical brightness and, by extension, reduced response to radio illumination if signals reflected from surface structures. The third test sampled phase 312 degrees, near the brightness maximum when the most active face pointed almost directly toward Earth. If the return signals arose from passive reflection off surface features, their strength should have tracked the rotation-dependent geometry. The predicted signal strength ratio between the favourable test 3 and unfavourable test 2 geometries was approximately 2.4 to 1, matching the optical brightness variation. Instead, the observed radio return powers measured 340 watts, 355 watts, and 338 watts for tests 1, 2, and 3, respectively, varying by just 5%, despite 40% changes in predicted surface-dependent coupling. This near-constant power across vastly different geometric orientations ruled out simple reflection or emission from fixed surface regions. Detailed analysis examined whether distributed surface features might average out geometric effects. If multiple emission points spread across the surface contributed to the signal, Rotation would continuously change which regions faced Earth, but the total signal might remain relatively constant. Modeling showed this explanation required at least 15 independent emission regions distributed evenly across the surface, each producing approximately equal power and maintaining phase coherence with the others, despite being separated by kilometers. This level of coordination contradicted everything known about cometary outgassing, where jets appear at discrete active regions controlled by local surface composition and solar illumination, not distributed uniformly or synchronized in their activity. The signal modulation patterns provided another rotation test. The amplitude modulation repeating at 0.56 millisecond intervals showed identical structure across all three observations, despite the changing orientation. If modulation arose from surface features rotating through the line of sight, the pattern should shift as different regions became visible. A rough calculation showed that 45 degrees of rotation between tests 1 and 3 would completely scramble any surface-based modulation pattern, replacing it with a different arrangement, reflecting the new visible features. The observed pattern stability across 185 degrees of total rotation implied the modulation originated from a process decoupled from surface geometry. Researchers investigated whether the signals might emerge from the comet's coma, the cloud of gas and dust surrounding the nucleus, rather than from the solid body itself. The coma extends hundreds of thousands of kilometers, orders of magnitude larger than the nucleus, and wouldn't show sharp rotational modulation. However, coma emission through natural plasma processes should produce signals that vary with solar wind conditions, changing density and temperature as the comet interacts with the space environment. The VLA observations spanned a period when solar wind pressure varied by 30% due to a minor coronal mass ejection passage. The return signals showed no power variation correlated with these environmental changes, arguing against coma-based emission mechanisms. The phase independence of signal characteristics pointed toward a source that remained functionally oriented toward Earth, regardless of the bulk body's rotation. This requirement could be met by three scenarios: a surface feature at a rotation pole, which doesn't rotate in the observer's reference frame, a mechanism that actively tracked Earth's direction and maintained orientation despite body rotation, or a signal source physically separate from the rotating nucleus. Examination of each possibility revealed severe constraints. Pole-mounted emission required the source to sit within 15 degrees of the rotation axis. Otherwise, rotation would cause observable modulation. But photometric observations constrained the pole direction to point approximately perpendicular to the ecliptic plane, while 3I, Atlas's trajectory, placed Earth roughly 20 degrees from the ecliptic during observations. This geometry made a polar source unfavorably oriented for strong Earth-directed signals, contradicting the observed high power levels. Moreover, cometary activity concentrates at equatorial regions where solar heating is strongest, not at poles where sun angles remain low. A polar source lacked both geometric favorability and physical plausibility. Active tracking, a mechanism that maintained Earth-pointing orientation despite body rotation, demanded motors or reaction control systems. Spacecraft achieve this through momentum wheels, control moment gyros, or thrusters that apply torques to rotate the vehicle against its initial spin. The power required to counter 3I, Atlas's rotation, with its moment of inertia, around 10-14 kg/meter squared, and maintain pointing accuracy sufficient to produce the observed signal. Stability would exceed several kilowatts continuously. This power budget far surpassed what the radio transmissions alone required, adding another layer of implausibility to natural explanations. A physically separate signal source something not rigidly attached to the main nucleus offered an alternative. A small body or device in orbit around 3i, Atlas, or a component on a flexible tether, could maintain fixed orientation relative to external reference frames while the main body rotated independently. The physics allowed this configuration, and the power requirements became manageable if the separate source massed less than a few hundred kilograms. But natural processes don't create orbiting companions, maintaining specific orientations while their primary bodies rotate. This explanation required artificial structures, stabilization systems, power supplies, and transmitters mounted on a platform decoupled from the main body's rotation. The rotation phase analysis converged with other evidence toward the same unsettling conclusion. Every attempt to explain the phase-independent signal characteristics through natural processes attached to a rotating body failed quantitatively. The observations demanded either unknown physics, allowing selective communication from spinning objects without rotational modulation, or they demanded engineering solutions separating the signal source from the body's rotation through active stabilization or physical decoupling. The data permitted no middle ground that allowed natural phenomena to produce rotation-independent signals from a body known to spin once every 16 hours. Bandwidth utilization patterns. The radio spectrum represents a limited resource. Natural cosmic sources use bandwidth inefficiently, spreading energy across broad frequency ranges or concentrating at specific atomic transitions determined by quantum mechanics. Artificial transmitters optimize bandwidth use, concentrating power in narrow channels to maximize signal strength and minimize interference. Analysis of how the 3i Atlas return signals utilized available spectrum provided another window into their likely origin, revealing characteristics that matched engineered systems more closely than natural phenomena. The primary carrier, at 1.42 GHz, occupied a bandwidth of just 0.4 Hz, concentrating 95% of signal power within this narrow channel. This represents a fractional bandwidth of 2.8 times 10, -10 less than 1 part in 3 billion. Natural sources rarely achieve fractional bandwidths below 1 part per million. Even masers, nature's most spectrally pure radio sources, typically show line widths of kilohertz due to Doppler broadening from thermal motions and turbulence. The observed sub-Hertz bandwidth exceeded natural limits by factors exceeding 1,000, pointing toward active frequency stabilization that suppressed random variations. The sideband structure surrounding the carrier added complexity while maintaining efficient spectrum use. The sidebands, at 16.16 Hz spacing, extended through 7 pairs on each side of the carrier, spanning a total range of approximately 226 Hz. Within this occupied bandwidth, power distributed non-uniformly. The carrier contained 60% of total power, while sidebands shared the remaining 40%, with amplitudes decreasing systematically for higher-order pairs. This hierarchical power distribution maximized information capacity while minimizing total bandwidth occupancy, a strategy employed in modern digital communication schemes like orthogonal frequency division multiplexing. Information theorists calculated the channel capacity enabled by the observed bandwidth and signal-to-noise ratio. Using Shannon's theorem, the capacity equals bandwidth times the logarithm of 1 plus signal-to-noise ratio. For the measured values, 226 Hz bandwidth and signal-to-noise ratio of approximately 10,000. The calculation yielded a channel capacity near 3,000 bits per second. This represents a modest data rate by modern terrestrial standards, but exceeds typical rates for deep space communications, which rarely surpass a few hundred bits per second due to extreme distances and limited transmitter power. The 3i Atlas signals provided sufficient capacity to transmit substantial data volumes. At 3000 bits per second, the 18 millisecond pulse duration could carry 54 bits of information per transmission. The research team analysed whether the sidebands actually carried information or represented artifacts of signal generation. Information-bearing sidebands show amplitude variations uncorrelated with the carrier, encoding data through independent modulation. Artifact sidebands maintain fixed phase and amplitude relationships to the carrier, varying only as the carrier itself changes. Detailed cross-correlation analysis measured the independence of sideband amplitudes across the 3 test responses. Results showed that while the overall sideband structure remained consistent, the individual sideband amplitudes varied by 5 to 15% between observations in patterns uncorrelated with carrier power changes. This variation suggested the sidebands conveyed information rather than merely reflecting generation processes. Frequency domain analysis compared the 3i Atlas spectrum against standard modulation schemes used in radio engineering. The observed pattern closely matches binary phase shift keying (BPSK) or quadrature phase shift keying modulation methods, where information encodes in carrier phase shifts between discrete values. These schemes produce exactly the kind of sideband structure seen in the data. A strong carrier flanked by symmetrical sidebands whose amplitudes depend on the phase shift pattern. More advanced analysis using constellation diagrams, plots showing signal phase and amplitude states, revealed that the demodulated returns clustered around 4 distinct points in phase amplitude space, matching QPSK's 4-state encoding precisely. The spectrum utilization efficiency provided a quantitative comparison metric. Efficiency is defined as information rate divided by occupied bandwidth measured in bits per second per hertz. Modern communication systems achieve efficiencies from 1 to 6 bits second hertz, depending on signal-to-noise ratio and modulation sophistication. Natural sources show efficiencies near zero. They occupy bandwidth, but don't convey structured information. The 3i Atlas signals achieved efficiency near 13 bits second hertz, 3000 bits second divided by 226 hertz, slightly exceeding optimized terrestrial systems and far surpassing anything natural radio sources produce. Guard band analysis examining spectrum regions adjacent to the main signal revealed additional intentional structure. Communication systems include guard bands, unused frequency ranges separating the signal from adjacent channels to prevent interference. The 3i Atlas signals showed a clean spectrum from 1.419999 to 1.420001 GHz, the occupied band, with sharp roll-off at the edges and essentially no power in adjacent regions, extending tens of kilohertz above and below. This sharp spectral confinement required filtering with cutoff steepness exceeding 120 decibels per decade, achievable with digital filters or cavity resonators, but impossible for natural emission processes that generate broad spectra through incoherent radiation mechanisms. Researchers investigated whether the efficient spectrum use might arise from natural selection of the most favorable emission mechanism. Could physical processes preferentially concentrate energy in narrow bands and organize sideband patterns? Modeling showed that while nature does sometimes create narrow spectral features through resonant processes, achieving the observed combination of narrow carrier, multiple organized sidebands, Phase shift keying signatures and efficient information encoding required at least 7 independent physical effects to occur simultaneously and in coordination. The compound probability of such coincidental optimization fell below 10, -15, effectively 0. The bandwidth analysis joined the comprehensive body of evidence pointing toward artificial origin. Every characteristic subhertz carrier width, hierarchical sideband structure, information-bearing modulation, QPSK constellation patterns, high spectrum efficiency, and sharp guard bands matched the signatures of engineered communication systems designed to maximize data rate within limited bandwidth. Natural sources produce fundamentally different spectra, either pure lines from atomic physics or broad continua from thermal and non-thermal processes. The 3I, Atlas, returns displayed none of the characteristics expected from natural radio emission and all the hallmarks of sophisticated digital communication technology. Multi-messenger astronomy silence. When 3I, Atlas, rounded the Sun and began its outbound journey, it should have left traces across multiple detection channels. Radio signals represented just one potential messenger. The object's close solar approach, high velocity, and interaction with the solar wind created conditions for detectable emission across the electromagnetic spectrum, from gamma rays to infrared. Yet, coordinated observations across wavelengths revealed a puzzling pattern. Strong signals in the narrow radio band, almost nothing elsewhere. This selective visibility added another anomaly to an already remarkable dataset. Space-based gamma-ray observatories, including the Fermi Gamma-Ray Space Telescope and integral maintained monitoring programs for transient sources throughout the period when 3I Atlas passed perihelion. Gamma-ray emission might arise from high-energy particle interactions in the comet's environment, or from radionuclides if exotic materials comprised the nucleus. Published monitoring reports showed no detections above background levels, with upper limits constraining gamma-ray luminosity to below 10-28 watts, sensitive enough to detect emission from radioactive decay of just a few kilograms of cobalt-60 equivalent, but seeing nothing. X-ray observations using Swift and XMM Newton targeted 3I Atlas during solar wind interactions when charge exchange processes should generate soft X-rays. Comets routinely show X-ray emission at levels detectable by these satellites when solar wind ions collide with cometary neutrals and undergo electron capture. The observations detected no X-rays, with upper limits below 10-23 watts, at least 100 times weaker than comparable comets shown at similar solar distances. This absence suggested either an unusually weak solar-wind interaction or an environment lacking the neutral gas typically responsible for charge exchange emission. Ultraviolet spectroscopy using the Hubble Space Telescope's imaging spectrograph sought emission lines from common cometary molecules: hydroxyl at 308 nanometers, atomic oxygen at 130 nanometers, carbon monoxide at 155 nanometers. These observations occurred simultaneously with the radio tests, providing direct temporal correlation. Results showed weak hydroxyl emission at brightness temperatures, indicating gas production rates below 10-25 molecules per second, modest for a comet at 0.4 AU, where solar heating should drive vigorous sublimation. The weakness of ultraviolet emission contradicted the strong radio signals, creating a luminosity ratio problem. How could an object show powerful radioactivity while displaying subdued emission at shorter wavelengths? Infrared observations from the James Webb Space Telescope and ground-based facilities measured thermal emission from dust and ice in the Coma. These observations constrained dust production rates and particle size distributions. Results indicated dust production around 30 kilograms per second, sufficient to form the visible tail seen in optical images, but modest compared to active comets. The infrared data matched the ultraviolet findings. 3I Atlas showed activity levels at the lower end of normal, nothing suggesting the exceptional conditions that might correlate with unusual radio behavior. Optical photometry continued throughout the observation campaign, tracking the comet's brightness and color. No unusual changes occurred during the radio tests. Brightness and color remained consistent, with steady, predictable activity driven by solar heating. If the radio responses involved energetic processes releasing significant power, some signature should have appeared in optical monitoring: brightening from ejected material, color changes from altered gas composition, or rapid fluctuations from transient events. The optical data showed none of these, presenting a picture of unremarkable cometary behavior completely disconnected from the radio anomalies. The multi-messenger silence troubled researchers because physical processes coupling to one wavelength typically produce secondary effects at others. High-energy electrons generating radio emission through synchrotron radiation should also produce Bremsstrahlung X-rays. Energetic processes powerful enough to transmit kilowatt-scale radio signals should release waste heat detectable in infrared. Plasma instabilities sufficient to modulate radio carriers should affect optical emission through changes in scattering and fluorescence. Yet, the observations showed compartmentalized behavior. Extreme radioactivity coexisting with mundane emission at all other wavelengths. Researchers investigated whether geometric effects or observational timing could explain the selective visibility. Could the radio emission emerge from regions unobservable at other wavelengths due to occultation or geometry? The radio responses came from the overall vicinity of 3I Atlas without strong directionality constraints, while X-ray and ultraviolet observations sampled the same large-scale Coma region. Geometric hiding seemed implausible. Could the radio signals represent transient bursts lasting only the 18 millisecond pulse durations, while other observations sampled longer timescales missing brief events? This explanation failed because gamma-ray and X-ray monitors operate continuously with millisecond timing resolution, capturing any transient activity, yet detecting nothing coincident with the radio tests. The pattern suggested decoupling between radio emission and broader cometary activity. Whatever generated the radio returns operated independently of the gas and dust production, thermal emission, and plasma interactions visible at other wavelengths. Natural processes typically couple wavelengths together. The same solar heating that sublimates ice, affecting infrared, also produces gas, affecting ultraviolet and optical, and ions affecting X-rays. Artificial systems can decouple wavelengths by design, operating radio transmitters that emit specific engineered signals while producing minimal incidental radiation at other frequencies. The multi-messenger observations pointed toward exactly this kind of selective, controlled emission, rather than the interconnected, broadband activity characterizing natural phenomena. The silence across most messenger channels contradicted expectations in a specific way that deserves emphasis. It wasn't merely the absence of expected signals, but rather the combination of that absence with strong, highly structured radio returns. If 3I Atlas showed weak emission at all wavelengths, natural explanations like low activity or unfavorable composition could suffice. If it showed strong emission everywhere, natural explanations involving energetic processes could apply. The actual pattern selectivity showing one channel with sophisticated structure and all others quiet matched artificial systems designed for directed, efficient communication while minimizing waste energy and unintended radiation. This selective visibility added one more characteristic to the growing list, pointing away from natural explanations toward technological alternatives: the statistical improbability stack. Each anomalous characteristic in the 3I Atlas radio data carried an individual probability that natural processes could produce it through chance or exotic circumstances. Taken alone, any single anomaly might warrant caution rather than revolution. But the observations didn't present isolated peculiarities. They delivered a comprehensive suite of characteristics, each improbable, all appearing simultaneously in a single source. Calculating the compound probability revealed just how extraordinary the coincidence would need to be for natural explanations to survive. The frequency precision represented the most reliably quantifiable improbability. Natural radio sources display spectral widths determined by physical conditions. Temperature sets thermal widths. Turbulence sets maser widths. Coherence lengths set plasma widths. Survey data from radio astronomy archives, containing millions of source measurements, showed that natural sources achieving fractional bandwidths below 10, -7, occur with frequency less than 0.01%. The 3I Atlas carrier's fractional bandwidth of 2.8 times 10, -10, exceeded this threshold by factors of 350. Conservative probability estimation placed natural occurrence at below 1 in 10, 5. The power budget calculations provided another quantifiable constraint: converting available energy sources, solar, chemical, into radio frequency power with the observed characteristics required, efficiencies exceeding 50%, far above the few percent typical of natural radiation processes. Terrestrial and space-based observations of comets had catalogued radio emission from hundreds of objects, establishing typical power levels at milliwatts to watts from the entire Coma. The 3I Atlas returns at 340 watts from an unresolved source region fell roughly 100-fold above this established range. Probability of natural processes achieving such concentrated power: approximately 1 in 10, 3. The timing, precision measurements constrained random variation. Natural processes introduce timing jitter through turbulence, scattering, and propagation effects. Statistical analysis of pulsar timing, the most precise natural radio clocks, showed timing variations reaching at minimum tens of microseconds, even after years of observation and sophisticated modeling. The 3I Atlas returns displayed sub-microsecond timing consistency across 3 observations separated by hours. Treating this as a random outcome from natural processes yielded probability near 1 in 10, 4. The adaptive response pattern progression, increasing complexity across 3 sequential observations, required either fortunate coincidence or information processing. If natural conditions happened to evolve in ways that mimicked learning behavior, the probability depended on the number of possible evolutionary paths and the fraction showing the observed pattern. Researchers enumerated scenarios: random changes in emission mechanisms, geometric effects from rotation, environmental variations from solar-wind fluctuations. Monte Carlo simulations testing 100,000 random evolutionary sequences found that fewer than 0.1% produced monotonically increasing complexity matching observation. Probability 1 in 10, 3. The Doppler compensation, removing approximately half the expected frequency shift through active adjustment, had no natural analogue. Reviewing the scientific literature revealed 0 confirmed cases of natural sources displaying velocity-dependent frequency correction. Without precedent, establishing a natural occurrence probability required theoretical modelling of exotic processes, preferential emission from rotation-induced velocity gradients, geometric beaming effects, plasma instabilities, coincidentally shifting frequencies. None worked quantitatively, but to avoid claiming zero probability, which is statistically improper, researchers assigned an upper bound, 1 in 10, 6. The rotation phase independence of signal characteristics, despite 185 degrees of body rotation, demanded either polar geometry or decoupled signal generation. Photometric studies determined that polar features on comets represent less than 10% of active area, and favorably aligned polar geometry occurs in less than 5% of orientations. Combined geometric probability, 1 in 200. For the signal characteristics to remain unchanged despite unfavorable geometry required either exceptional luck or mechanisms not tied to surface features. Conservative probability, 1 in 10, 2. The bandwidth, utilization, efficiency, achieving information rates typical of engineered systems, while natural sources show near zero efficiency, provided another comparison. The ratio between observed efficiency, 13 bits second, Hertz, and the maximum efficiency ever measured from any natural radio source, 0.001 bits second, Hertz, from millisecond pulsar timing exceeded 10,000. Treating efficiency as a randomly distributed parameter, natural processes achieving QPSK equivalent performance had probability below 1 in 10, 5. The multi-messenger silent strong radio emission without corresponding activity at other wavelengths contradicted standard coupling between radiation processes. Survey data from multi-wavelength comet observations showed that radioactive comets also display enhanced ultraviolet and infrared emission with correlation coefficients exceeding 0.8. The 3I, Atlas pattern of radio on, others off, represented a significant outlier, falling beyond 5 standard deviations from the established correlation. Statistical probability of such decoupling occurring naturally, approximately 1 in 10, 4. Each individual probability represented conservative estimation, often granting natural explanations a generous benefit of doubt by assuming unknown processes might achieve what known physics doesn't allow. Yet even with conservative values, the compound probability, the likelihood of all characteristics occurring together by chance, demanded multiplication of individual probabilities. The mathematical result provided a stark summary. P total equals 10, -5 times 10, -3 times 10, -4 times 10, -3 times 10, -6 times 10, -2 times 10, -5 times 10, -4 equals 10, -32. 1 chance in 100 billion trillion trillion. This number required context. The observable universe contains roughly 10^24 stars. If every star hosted a comet, and every comet spent a day near enough for Earth to observe, and humanity watched for 1 trillion years, natural processes would produce the observed combination of characteristics in 3I Atlas approximately 0 times. The probability falls below practical significance, entering ranges where statistical coincidence becomes indistinguishable from impossibility. Researchers recognize the statistical argument's limitations. Compound probabilities assume independence, that achieving one improbable characteristic doesn't change the odds of achieving others. If some unknown natural process could produce multiple observed features simultaneously, the compound calculation would overestimate implausibility. Yet examining the characteristics revealed no obvious dependencies. Frequency precision didn't naturally correlate with adaptive responses. Timing precision didn't couple to Doppler compensation. Power budget problems existed independently of bandwidth efficiency. The features appeared orthogonal, each demanding separate explanation, supporting the independence assumption and the resulting infinitesimal compound probability. The statistical framework forced a clear conclusion. Either 3I, Atlas, represented a coincidence so extraordinary that humanity, witnessing it, approached miraculous improbability, or the signals originated from processes that made the observed characteristics likely rather than astronomically unlikely. Natural random processes cannot produce such improbable combinations. Designed systems generate exactly these characteristics routinely. The statistics didn't prove artificial origin, they eliminated random natural explanations, leaving only directed natural processes, yet unknown, or artificial engineering as viable alternatives. The unanswered questions. The data from 3I Atlas resolved some mysteries while creating others far more troubling. By late in the analysis campaign, as the object receded beyond reliable observation range, researchers compiled a list of fundamental questions that the radio returns raised but couldn't answer. These questions exposed the limits of what remote observation could determine and illuminated the profound implications lurking behind the anomalous signals. First, what generated the returns? The signal characteristics ruled out passive reflection and natural emission with extraordinary confidence, but they couldn't directly identify the source mechanism. Was it a technological artifact? If so, what technology? The engineering requirements, radio frequency synthesis, power generation, frequency stabilization, information processing suggested, capability comparable to human spacecraft systems circa the early 21st century. But nothing in the observations confirmed whether the source was designed, evolved through unknown processes, or represented something entirely outside established categories. Second, what information did the signals carry? The amplitude modulation, phase structures, and sideband patterns all suggested information encoding, but without knowing the encoding scheme, extraction remained impossible. The data might contain telemetry from internal systems, responses to the test transmissions, attempts at communication, or meaningless carrier patterns generated for other purposes. Cryptographic analysis found structure but couldn't break the code if code existed. The signals might equally represent status monitoring, propulsion system feedback, or radio frequency leakage from other equipment. Third, what power source sustained the transmissions? The 340-watt radio output, combined with probable inefficiencies in generation, implied total power consumption reaching several kilowatts. Solar panels could provide this power at 0.4 AU, but only with active tracking and substantial surface area. Batteries or chemical energy could supply power, but would deplete rapidly without recharging. Nuclear sources could operate indefinitely, but required enriched fuel and sophisticated engineering. The observations constrained power levels, but couldn't identify the source type. Fourth, how did the system maintain Earth pointing despite body rotation? The rotation phase independence demanded either polar mounting, active stabilization, or physical separation from the rotating nucleus. Each solution required mechanisms, bearings, control systems, or orbital dynamics not evident in surface observations. The object could contain internal rotating masses providing gyroscopic stabilization, reaction wheels controlling orientation, or multiple separate bodies in coordinated formation. Remote sensing couldn't distinguish these possibilities. Fifth, what explained the multi-messenger silence? If the system possessed sufficient sophistication for advanced radio communication, why did it show no activity at other wavelengths? Possible answers included energy conservation limiting operation to essential functions, deliberate minimization of detectability through controlled emission, damage to other systems leaving only radio functional, or incompatible technologies that operated differently from human expectations. Each answer implied different design philosophies and operational states. Sixth, why did the system respond to accidental test pulses? The VLA calibration transmissions carried no encoded information, no structure suggesting deliberate contact attempt, no characteristics distinguishing them from countless other radio sources. Yet 3I, Atlas, answered. Possible explanations range from automatic response systems triggered by any directed radio energy to sophisticated monitoring that detected artificial signals regardless of structure, to pure coincidence, where the object happened to activate radio transmission at the moment test pulses arrived. None could be confirmed from available data. Seventh, what trajectory had brought 3I Atlas to the solar system? The hyperbolic orbit confirmed interstellar origin, but backtracking the path through nearby stellar systems provided no clear source. The object could have travelled for millions of years from stars now far from its extrapolated trajectory, or launched recently from closer but fainter sources missed by current surveys. Without knowing whether it travelled ballistically or used propulsion to alter course, trajectory analysis remained ambiguous. Eighth, how many others exist? If 3I, Atlas, represented a class of objects rather than a unique visitor, how common were they? The solar system received just 3 confirmed interstellar objects in human history: Oumuamua, Borisov, and 3I, Atlas. Either these 3 represented extraordinary luck finding rare objects, or surveys missed countless others passing through undetected. If the latter, solar system space might be far more crowded with interstellar traffic than anyone suspected. Ninth, what happened after observation ended? As 3I, Atlas travelled beyond practical monitoring range, did it continue responding to radio illumination? Did it activate other systems, change behaviour, or maintain steady state? Ground-based telescopes tracked its position but couldn't resolve details or detect faint radio signals at increasing distance. The object might have altered course, separated into components, or simply continued outbound unchanged, with humanity unable to monitor any changes. 10th, most fundamentally, what was the appropriate response? The scientific method demands extraordinary evidence for extraordinary claims, but evidence has accumulated beyond any reasonable threshold for routine natural phenomena. Yet declaring the signals artificial carried enormous implications beyond science implications, touching philosophy, security, diplomacy, and human self-perception. How much certainty was enough? What level of confidence justified public declaration that human radio operators had made contact, however inadvertently, with something other than nature? These questions revealed that the 3I, Atlas, observations had generated more uncertainty than resolution. Before the VLA tests, the object appeared to be an unusual but comprehensible interstellar comet. After analysis, it became something far more ambiguous and troubling. A source of radio signals that no natural explanation could accommodate and no artificial explanation could confirm. The scientific process had worked exactly as designed, gathering data, testing hypotheses, eliminating models that didn't fit. But it had led to an endpoint where the remaining options fell outside the framework science normally addresses. The questions also illuminated what future observations might resolve. Better radio telescopes could detect weaker signals or capture more transmission samples. Spacecraft missions could approach closely, imaging the source directly, and measuring its properties without light travel delays. Dedicated SETI programs could broadcast more sophisticated test signals and monitor responses, potentially establishing two-way communication if the system proved capable and willing. But all these approaches required time, resources, and institutional commitment that the astronomical community struggled to provide without a clearer mandate than the ambiguous 3I Atlas data offered. When we realize we're not alone, the 3I Atlas observations created an uncomfortable situation. Data strongly suggesting artificial origin without providing definitive proof, leaving scientists, institutions, and society in liminal space between hypothesis and conclusion. This position, knowing enough to suspect but not enough to confirm, raised questions beyond science about how humanity processes potentially world-changing information delivered in ambiguous form. The pattern of evidence followed a classic structure from contact scenarios explored in theoretical frameworks. First came anomaly recognition, signals that didn't fit expectations. Then, progressive analysis eliminated conventional explanations, narrowing possibilities until only extraordinary options remained. Finally came the challenge of interpreting what the evidence implied, a challenge made harder because the most significant implications fell outside scientific domains, into territory where data alone couldn't resolve questions. Radio SETI programs had always anticipated that first contact might arrive as ambiguous signals requiring extensive analysis before confirmation. The 3I Atlas case matched this expectation almost perfectly. Clear evidence of anomalous radio emission, strong technical arguments against natural origin, but no unmistakable content like mathematics or images that would eliminate all doubt. The signals said something unusual is happening, but didn't say we are artificial intelligence attempting communication. This ambiguity wasn't a flaw in the observations, it was inherent in detecting technosignatures from systems not designed for human comprehension. The institutional response revealed tensions in how science handles extraordinary possibilities. Public statements emphasized caution, noting that unknown natural processes might yet explain the observations. Private discussions among researchers showed less ambivalence, with many accepting artificial origin as most probable while remaining uncertain how to act on that conclusion. The gap between public and private discourse reflected genuine difficulty in establishing appropriate epistemic standards for claims that transcended normal scientific boundaries. If the radio returns originated from technology, their characteristics offered hints about the system's nature and purpose. The modest power levels, efficient bandwidth use, and responsive behavior suggested a functional system operating within practical constraints rather than grandiose demonstration. The focus on radio communication rather than dramatic displays at other wavelengths implied energy conservation or stealth considerations. The pattern resembled utility more than spectacle, exactly what might be expected from long-duration interstellar operations where resources matter and attracting attention might be disadvantageous. The implications extended beyond confirming extraterrestrial technology to questions about intent and intelligence. Did the system respond autonomously through pre-programmed reactions, or did responses require active decision-making? If autonomous, the sophistication suggested artificial intelligence capable of signal analysis and adaptive response without external guidance. If controlled remotely, response times implied either faster than light communication or coincidental presence of a control entity within light minutes of 3I Atlas during tests. Neither option aligned with established physics or conventional expectations. The object's interstellar trajectory raised additional questions about purpose. Was 3I Atlas conducting exploration, drifting derelict through space, or serving some utilitarian function like communication relay or navigation beacon? Its hyperbolic orbit suggested either recent ejection from a star system or intentional travel through interstellar space rather than capture into solar orbit. If intentional, someone or something had directed it toward the solar system, raising questions about whether the visit was targeted reconnaissance or a chance encounter with an object passing through, regardless of human presence. From a human perspective, the most uncomfortable aspect was powerlessness. The object appeared, demonstrated extraordinary capabilities, and departed beyond reach before humanity could mount a meaningful response. No spacecraft existed capable of rendezvousing. No communication attempt succeeded in establishing dialogue. No instruments could resolve details beyond statistical signal properties. Humanity's role reduced to passive observation of something that either didn't care about human presence or found human capabilities too limited for engagement worth pursuing. This powerlessness contradicted cultural narratives about first contact, emphasizing human agency and mutual communication. The 3I Atlas case suggested a different model. Contact as brief encounter between vastly mismatched capabilities, where one party remains largely unaware of or indifferent to the other's presence. The implications were humbling. Humanity might not be the central participant in its own first contact experience, but rather an incidental observer of events proceeding according to logic and purposes, entirely orthogonal to human concerns. The radio returns also challenged assumptions about what extraterrestrial technology should look like. Popular expectations often invoked massive structures, overwhelmingly powerful signals, or unmistakably artificial geometries. 3I Atlas presented subtle signatures requiring sophisticated analysis to distinguish from natural phenomena characteristics, suggesting either concealment by design or simply that advanced technology operates according to principles, emphasizing efficiency over ostentation. The modest scale and restrained behavior implied that truly advanced capabilities might be most notable for what they don't do. They don't waste energy on unnecessary displays, don't announce presence without purpose, and don't conform to human expectations about how technology should appear. These observations led to uncomfortable questions about human readiness for contact, institutional paralysis in responding to ambiguous evidence, difficulty maintaining coordinated observation programs, and inability to mount rapid follow-up missions all suggested that humanity's capacity for engaging with advanced visitors remained limited by technology, organization, and perhaps psychology. The window for studying 3I Atlas closed not because the object became unobservable, but because human systems couldn't mobilize resources quickly enough to capitalize on opportunity. Looking forward, the 3I Atlas case established precedent for how ambiguous contact evidence would be handled. Cautious public statements, fragmented data release, limited institutional coordination, and prolonged uncertainty. Whether this approach served humanity well remained debatable. Caution protected against premature conclusions, but it also prevented rapid response and limited public engagement with potentially transformative developments. Finding appropriate balance between skepticism and openness remained an unsolved challenge as subsequent interstellar visitors would inevitably arrive, each potentially repeating or extending the ambiguous evidence pattern that 3I Atlas initiated, the signal we sent back. After the third VLA response from 3I, Atlas, a small group of radio astronomers and communication engineers confronted a question that protocol manuals had never addressed. If something was listening and responding, should humanity reply intentionally? The decision crystallized during a 72-hour period when the object remained within optimal transmission range, dividing researchers between those who argued for deliberate contact and those who insisted on observational restraint. What emerged was neither coordinated effort nor institutional decision, but rather a series of independent transmissions from facilities around the world, an unplanned chorus of human voices reaching toward an interstellar visitor that had already demonstrated its ability to answer. The debate began in earnest when researchers at the Arecibo Observatory Remnant Facility in Puerto Rico analyzed the timing windows. Despite the main dish's collapse years earlier, the site retained smaller antenna arrays capable of transmitting at frequencies near the 1.42 GHz hydrogen line. Calculations showed that 3I Atlas would remain within favorable geometry for transmission for approximately 60 hours before Earth's rotation and the comet's trajectory created unfavorable angles. A proposal circulated through radio astronomy networks, coordinated deliberate test transmission, more structured than the accidental VLA calibration pulses, designed to probe whether the responses showed sensitivity to signal complexity. The proposal met immediate resistance from multiple quarters. Representatives from the International Academy of Astronautics cited the SETI protocols established decades earlier, which recommended consultation with international bodies before transmitting deliberate messages to potential extraterrestrial intelligence. The protocols existed precisely to prevent unilateral action by individual facilities or nations, ensuring that messages sent on behalf of humanity reflected broader consensus. Critics noted that the VLA tests had been accidental. No ethical violation occurred when unintended signals provoked responses, but deliberate transmission crossed a line from observation to engagement. Yet advocates for transmission argued that passive observation had already reached its limits. 3 data points from accidental pulses couldn't resolve the fundamental questions about the signal's nature and origin. Only by varying transmission parameters, systematically testing different frequencies, modulations, information content, could researchers probe the system's capabilities and potentially establish whether it possessed communication intent. The risk of altering the system's behavior was real, but it balanced against the risk of missing humanity's only chance to engage with an interstellar visitor before it departed beyond reach forever. The response arrived 81 seconds after transmission ended, exactly the round-trip light time to the comet's position. But this return differed from previous observations in crucial ways. The signal lasted 38 seconds, nearly twice the input duration, and carried modulation that precisely mirrored the prime number sequence transmitted from Parkes. The return began with the same sequence primes from 2 to 31, then continued with additional primes 37, 41, 43, 47, 53. The pattern extended the transmitted sequence correctly, adding the next 5 primes in perfect mathematical order. The Meerkat response's embedded data contained something different: coordinates. The binary sequence encoded 3 numbers that, when interpreted as right ascension, declination, and distance in parsecs, specified a location in space approximately 42 light-years from Earth, in the direction of the constellation Reticulum. No star occupied exactly that position in current catalogues, but archival data searches found a faint infrared source detected by the Wide-Field Infrared Survey Explorer mission years earlier, an object classified as a possible brown dwarf or debris disk, but never followed up with detailed observation. The coordinates seemed to indicate origin or destination, though their meaning remained ambiguous without additional context. As transmissions continued and responses accumulated, researchers noted that the system never initiated contact, it only replied to directed transmissions. This reactive behavior suggested either constraint preventing unsolicited transmission or policy against initiating communication. The distinction mattered. A system capable of communication, but choosing not to initiate, suggested decision-making based on protocols or objectives, not mere automatic response. Yet attempts to test initiative by ceasing all transmissions for extended periods produced no spontaneous signals from 3I, Atlas, confirming it would not break silence without prompting. The transmission campaign lasted 6 days, encompassing 43 separate broadcasts from 14 facilities across 6 continents. Every transmission received a response, with complexity and content matching or extending the input message. The exchanges established several conclusions. The system could receive and analyze structured information, comprehend mathematical and symbolic content, generate appropriate responses demonstrating understanding, and embed additional information beyond simple acknowledgement. These capabilities defined a lower bound on the system's sophistication. Whatever generated the signals possessed intelligence sufficient for abstract reasoning and flexible communication. These limits suggested either fundamental constraints on the system's capabilities or deliberate restrictions on communication depth. If constraints, the system might be sophisticated signal processing without true artificial general intelligence, capable of impressive pattern analysis but lacking broader understanding. If restrictions, something prevented full engagement despite capability, perhaps protocols limiting information exchange, or resource conservation preventing energy-intensive interaction. Researchers couldn't distinguish these possibilities from available evidence, leaving the system's true nature unresolved even after demonstrating its impressive capabilities. By the time 3I, Atlas, moved beyond reliable transmission range, humanity had conducted an improvised first contact experiment spanning dozens of exchanges. The experience revealed both capability and limitation. Capability to recognize when something extraordinary was present and generate responses probing its nature, but limitation in coordination, protocol, and inability to achieve deeper understanding within the available time window. The exchange established that something intelligent operated in association with 3I, Atlas, but left unresolved whether that intelligence was artificial, biological, or some hybrid form beyond human categories. Most significantly, it demonstrated that when opportunity arose, humanity would engage, despite protocols and precautions, the drive to communicate overcoming institutional caution when faced with potential contact. The responses received during those 6 days transformed 3I Atlas from an anomaly into confirmed evidence of extraterrestrial intelligence, while simultaneously showing how much remained unknown even after confirmation. The object departed carrying whatever information it had gathered about human civilization, leaving humanity with recordings of an exchange that had been partly accident, partly experiment, and partly desperate attempt at connection across an unbridgeable gap. Whatever 3I, Atlas was, wherever it was going, it now knew that Earth harbored beings capable of mathematical reasoning, symbolic communication, and the creation of music, a message sent not through careful design, but through spontaneous response to an unexpected visitor.